Hello everyone, welcome to the first lecture of week 10. In this week 10, we will explore maxima and minima and the application of these maxima minima in geometrical as well as our daily life uses. So, in use of the maxima minima using the derivative is one of the most influential topic in calculus. Why? Because it is applicable everywhere. That is why maxima minima is important. So, let us start with the formal definition, then we will go through the mathematical definition of maxima and minima. So, what is the formal definition? So, before going to the maxima and minima, what will be the most influential point for a function given in a closed interval? So, the three types of different points are there. One of the most critical point which has been used in a calculus is defined as a critical point of a function f is a point C in the domain D of f such that f dash of C equal to 0 or f dash of C does not exist. That means, so you have a closed interval a to b and a function is defined, then the such function has the critical point, we call it the critical point, f dash of C either exists and equal to, this is equal to and equal to 0, or f dash of C do not exist, right, does not exist. So, the point C is said to be the critical point of the function f. One of the example is given, f x equal to x cube plus x square minus x, a function is given and we have to find out the critical points. Take the f dash of x become 3x square plus 2x minus 1 and this is going to be 0. Equate this one and you will get the answer x equal to 1 by 3 and minus 1. So, now we have two critical points for that function, that is 1 by 3 and minus 1. Similarly, a function which is complex in a nature, x to the power 5 by 4 minus 2 x to the power 1 by 4 is given and you have to find out the critical points. So, find out f dash of x equal to 5 by 4 x to the power 1 by 4 minus 1 by 4 2x minus 3 by 4, right, and equate it is equal to 0. So, once you equate it, you will get the two value of x, that is equal to origin, that is 0 and 2 by 5, right. So, that will be your critical points for this function. Similarly, what is the local maxima and local minima? So, let me start with the local maximum or local maxima. A function f x is said to attain a local maximum at x equal to a if there exists a neighborhood delta a minus delta a plus delta of a such that f x is less than f a for each x belonging to that neighborhood and obviously x does not equal to a, or f x minus f a is less than 0 for all x belongs to that neighborhood. In such case, f a is called local maximum value of f x at x equal to a. So, look at the graph here, this is the local maximum, isn't it? I mean, it is maximum of each point. So, take a neighborhood. So, here let us say this point is a and we are taking a neighborhood here, delta neighborhood. So, this is the delta neighborhood, this will be the delta neighborhood, this point is a minus delta and this point is a plus delta. And now try to find out the function behavior. So, now we have to think about the function behavior in these two, in the neighborhood, these two end points of the neighborhood. So, each f x, as you can see here, this one is f a and each of f x, whatever you want to choose, just choose it. These all f x is less than, f of x is less than f of a, and it is true for a neighborhood which is a minus delta to a plus delta, right. And similarly, what will be the local minimum? So, here is the local minimum and as you can think about this as taking the local neighborhood and each f x of these values obviously it is greater than f of x is greater than f of a, right, for every x, and this will be a minimum one, and this will be the maximum one, right. So, local minimum is the same thing, f x minus f a, f x is always greater than f a, see here all these things are greater than f a, and in such a case f a is called the local minimum value of that function f x, and the point is called the local minimum value of f x, local minimum point of that f x. So, what are these properties? The points at which a function attains either the local maximum or the local minimum, known as the extreme points or turning points. These extreme points and both local maxima and local minimum value are called the extreme values of f x, right. So, here we have these are the extreme points, and in that case both are called extreme values of f x. Thus, a function attains an extreme value at x equal to a if f a is either a local maximum or either a local minimum. Consequently, at an extreme point a, f x minus f a keeps the same sign for all values of x in a deleted neighborhood, right. So, as you can see in this picture, so if you are looking for this one, so what will be happen? It will happen that you will see here the each value of f x is less than f a, that means f x minus f a is always less than 0, because f a is the maximum value, or looking at this point, and the sign is always the same, in a neighborhood, in that neighborhood a minus delta to a plus delta, we had seen right now. Similarly, for a local minimum f x minus f a is greater than 0. So, that is what it says, f x minus f a keeps the same sign for all values of x in a deleted neighborhood. This is the illustration of the same thing we had explained. The x coordinate of the point A, C, E are points of a local maximum. These points are the local maximum and these points are the local minimum, and their y coordinates are local minimum values. So, these are the local maximum values f x, this is the f x, this is the f x, right, and these are the local, okay. So, I have to change this color first. So, these are the local minimum values, these are the local minimum values, right. More example are given here. So, this is the point, this is the deleted neighborhood we have chosen here, and we try to find out the derivative or the slope of the tangent line at that point. So, it follows from the above definition that a is the point of local maximum of a function f, then in a neighborhood of a, graph f should be as on the right, right. So, this is our function and this is the graph, right. So, clearly f x is increasing, increasing and attained its maximum value with this neighborhood, in this neighborhood it is increasing, and is this neighborhood and decreasing in the right hand side, this is neighborhood it is decreasing, right. So, we had seen in a last lectures where we have seen that a function is said to be increasing function if f dash of x is greater than 0, or it is called a decreasing function when the first derivative of the function is less than 0. So, using the same thing in the left this neighborhood, this one will become greater than 0, the first derivative of the function f dash of x at any point in a minus delta to a is greater than 0, while in the right hand side f dash of x is less than 0 for any point in the right corner. So, this suggests that f dash of a must be, since one sign to another sign changes, and it is only possible when f dash of a is going to be 0. So, you crossing the line. Similarly, for a local minimum is also the same thing, and henceforth f dash of a equal to 0. And henceforth there is a very well established theorem for extreme value of a function in a neighborhood given of a neighborhood, right. So, a necessary condition remember this one, this is a necessary condition, not a sufficient condition. So, you have to be aware about necessary and sufficient condition. So, a necessary condition for f(a) to be an extreme value of a function f(x) is that f dash of a equal to 0 in case it exists. If it exists, f dash of a must be equal to 0, where extreme value, that means the maxima or minima, exist. So, what will be the proof? For the sake of definiteness, let us assume fc is the maximum value, or you can take the minimum value as well. Hence, there exists a delta such that fx minus fc, the point is fc here. So, this point must be c, not a, right, because we have chosen here c here. So, a necessary condition for f(a) to be an extreme value of a function f(x) is that f dash of a equal to 0 in the case it exists. So, for sake of definition, let us say a is here, and we try to find out a delta is greater than 0. So, we have a delta here and delta here, right. So, we have a neighborhood here, and fx is less than fc. In place of c, please read a. So, in place of c, please read a, because it is a typo where we have done this. Anyway, so f of x is greater than f a, f of x is less than f of a for every x belongs to where. So, here it is the maximum one, and the maximum one means the structure is like this, right. So, all these values are less than this. So, f x is always less than f a for the whole neighborhood a minus delta to a plus delta, and in case f dash exists, there are three possibilities: either f dash of a is greater than 0, f dash of a is less than 0, and f dash of a is equal to 0. So, we try to each one. So, f dash of a is greater than 0, then there exists an interval a to a plus delta 1, and such that every point of f x is greater than f of a, which contradicts the fact that f of a is maximum value, right. So, this is the contradiction, it cannot happen. Similarly, we can see that f dash of a is less than 0 is also not going to be hold. So, it is a contradiction again, and hence the possibility is the only one, that is f dash of a equal to 0. And these are the remark. This result state that if derivative exists, it must be 0 at extreme value. A function may, however, attain the extreme value without being derivative thereat, right. So, it may be possible that function does not have the derivative at the given point, but it must have the maxima or minimum value at that point. Here is the one example, as you can see here, this is the modulus x, and what will be the derivative at this point? The function is not derivative, it is a continuous function at x equal to 0, but not a derivable function here, right. So, modulus of x attain the minimum value at x equal to 0, whereas the derivative does not exist. The condition is only necessary condition, and for the point x equal to a to be an extreme point, it is not sufficient. That means, f dash of a does not necessarily imply that x equal to a is an extreme point. No, never be. There are functions for which the derivative vanish at a point, but do not have an extreme value thereat. Can you find out such function where f dash of x is going to be 0, but the function does not have maximum or minimum value? Do you think about this, or are you assuming this? Okay, so let me give you the answer in the next slide. Look at this function. This is f dash equal to x cube and f dash of 0 equal to 0, but at x equal to 0, the function does not attain an extreme value. See, this is not the extreme value. In fact, on the left of the x equal to 0, the curve is concave, and on the right hand side it is concave, right. This one is concave, and that is what it is, right. So, upward is the concave here, and the downwards is the concave up, and this is concave down, right. So, this is the concave up. So, concave down, concave down, right. That is, concavity of f(x) changes as x increases through 0. Such points are called points of inflection. The points where f dash of x is equal to 0 does not imply the point as extreme value, that is maxima or minima, then such a point is called point of inflection. So, point of inflection is the another term where f dash of a is going to be 0, but function f x does not attain maxima or minima, right. If x equal to c is a point of inflection of a function f x, then f dash of c equal to 0 and f double dash of x changes its sign as x increases through a, right. So, x equal to c, x equal to a is a point of inflection of a function f x, then f dash of a is equal to 0 or f double dash of x changes its sign as x increases through a. Geometrically, the above condition means that the tangent to the curve y equal to f x at a point where the ordinate is maximum or minimum is parallel to the x axis, right. As discussed in remark 2, that all x for which f dash of x equal to 0 do not give us an extreme value. The values of x for which f dash equal to 0 are called the stationary point or turning points, and the corresponding values of f x are called the stationary or turning values of f x, right. So, it is not going to be a extreme value, but it is called a stationary or turning points. The values of x for which f dash of equal to 0 or f dash of x does not exist are known as the critical points, right. So, we have two things, one is the critical points and one is the point of inflection, where you have seen the maxima and minima and point of inflection, and then again you have called those points in a different way, where the values of f x equal to 0 are called those values which do not give the extreme value are called the turning points or stationary points. Now, another term has been arises, that is if I have a local maximum or local minimum, then there must be some of the thinking about the global maxima or global minima. So, what is the global maximum? Let f x be a real function defined on interval I, then f x is said to have the global maximum value in I if there exists a point A in I such that f x is less than or equal to f a for all x belongs to I. In such a case, the number f a is called the maximum value of f x in the interval I, and the point A is called the point of maximum value of f in the interval. Now, we are not talking about the point and its deleted neighborhood, we are talking about the whole interval. So, now look at the very interesting thing here is that interval I is the closed interval, let us say closed interval here, and we are looking for each function any point for here and corresponding f x, if this point, okay, so here is a, so something like if this point, let us say this point, so this point here, if this point in that interval I is the maximum value, then it is always maximum, that means the greater than of each of these numbers, each of these corresponding value of f of x, right. So, f of x is always less than or equal to f a for all the interval. So, let us say we have to practical examples for that. Consider the function f given by f x equal to minus x minus 1 ka whole square plus 10, and clearly the domain f is what? If this function is defined for each real numbers, put x equal to 1, x equal to minus 1 and so on, you will get some finite number, that is why the domain is the whole real number. We observe that minus of x minus 1 ka whole square, this quantity is positive. So, minus of this is always less than or equal to 0 and equal to 10. So, f of x is now is less than or equal to 10, and that means f x is less than or equal to, how you will get the 10. So, putting the value, this value is going to be 0. So, that will give you x minus 1 equal to 0, x minus 1 ka whole square equal to 0. So, this will give you x equal to 1, right. So, that means f of 1 here, f of 1 equal to 10. So, f of x is always less than or equal to f of 1 for each x belongs to the real number. So, we have find out the domain for that value, the function is defined in that domain, and then we have find out one point, that is x equal to 1, that is f of 1, and f of 1 is always greater than or equal to f x for the whole real number. So, therefore, f1 equal to 10 is the maximum value, and this function is called the global maximum value. There is no other one which is going to be beat that one. So, and what is the global minimum? Let f x be a real valued function and in an interval, and if you find out f x is always greater than or equal to f a for all x belongs to I in the whole interval. If you are taking this interval, then each value is a sum of the value, let us say this f of a or some value is always less than or equal to f of x, then this will be a global minimum. So, consider a function f x equal to x square plus 5. Here domain is d is what? D is every real number. So, d is total r minus infinity to infinity minus infinity to infinity here, right. And let us say x square is always greater than or equal to 0. We have seen this, right, and this is greater than or equal to 0. So, x square plus 5 is also greater than 5, and this one will be the function. So, f x is greater than or equal to 5, and 5 can be written as f of 0. So, that means we have find out f 0 equal to 5. So, this means f 0 equal to 5 is the minimum value of the function in the whole interval, and that is called a global minimum value. But at which point, what will be the point at which the function has the global minimum value, that is equal to x equal to 0. This is equal to x equal to 0. So, in the above discussion, we have seen that f x equal to minus x minus 1 ka whole square plus 10 has the maximum value, but it does not attain the minimum value anywhere, because minus x minus 1 ka whole square plus 10 can be made as small as we please. And the function f x equal to x square plus 5 attains the minimum value 5 at x equal to 0, but it does not attain maximum value, because you can choose the maximum value as you want, as you think, right. So, that is why even it has minimum value and does not have the any maximum value. Similarly, this is the graph for maxima and minima and the global maxima and global minima. So, look at this graph first. How many points? Let me change first the color of this pen, and now can you identify how many terms or how many points which is the local maximum? So, wherever you find out the hump, that means there is a concave down and concave up, concave down or concave up, you will find out this is the maximum. So, this and this, right. Any other one? No. So, how many points you will have? You have a 3 value and 3 points where you will find out the local maximum, and let us say this point is first 1, this point is a. So, 1 x equal to 1, x equal to a, x equal to let us say 2, right, or you can name like c or d, right. So, let us say c and let us say d, right. So, we have a 3 points x equal to c, a and d, which are going to give me the local maximum. And how many points you will identify for local minimum, right. So, for minimum, let us say this point and this point. So, we have here C E and this one will become B. So, x equal to E and x equal to B. These are the local minimum points, right. Now, find out those values. That means you have to find out f of C, f of A, f of D first, right, and you will find out f of E, f of B. If these value, among these value, which one is the maximum one, that will give you the global maximum. So, finding out this one, as you can see, f of a is the global maximum, the highest one. Similarly, f of between the fe and fb, we have the fv, which has the minimum value. So, that is why this will become global minimum. So, that is the criteria how to identify the global maximum and global minimum among the local maximum and local minimum. So, now take some examples and try to find, and this has happened because we have chosen our interval, and f of a is the maximum value for the whole interval. Similarly, f of b is the minimum value for the whole interval. That is why we have named it as a global maxima or global minima. So, f of x attains both maxima and minima. Consider the function f x equal to sin x, and sin x always has the value minus 1 to 1 in x equal to 0 to 2 pi. So, f pi by 2 equal to 1 and f 3 by pi by 2 equal to minus 1. So, that means the f x has the boundary as f 3 by 2 and f pi by 2. So, f x attains both the maximum value as well as the minimum value minus 1 in the interval 0 to 2 pi. So, these points x equal to pi by 2 and 3 pi by 2 are respectively called the points of maxima and minimum, right. Consider the function f x equal to x cube. We had already done this one, but here it is given that it is defined only in minus 2 to 2. So, minus 2 to 2 it is defined. Clearly, it is an increasing function on the given interval minus 2 to 2. So, it should have the minimum value at a point closest to minus 2 on its right and maximum value at a point closest to 2 on the left. In fact, it is not possible to locate such point as shown in the figure. You cannot find out where is going to be the maximum or where is going to be the minimum one. Therefore, f x equal to x cube has neither the maximum value nor the minimum value. Let me again give you some of the idea how we are reaching at that conclusion that f x equal to x cube neither has the maximum value or minimum value. So, since we have taken is minus 2 to 2 right here. So, as a guess you have a minimum value at a point minus 2, because f of minus 2 equal to minus 2 ka whole cube equal to minus 8, and f of 2 equal to 2 ka whole cube is equal to 8. So, that means here closest to the this one maximum value on its right. So, this point it must have the some maximum value, but you cannot find out which one, right. Similarly, for 2 this point you have a minimum, but you cannot find out the which one, and that is why it is neither a maximum nor a minimum. Now, find the absolute or global, both naming are correct. So, a maximum value and absolute global or minimum value of f x equal to 3 x per power 4 minus 4 x cube minus 12 x square plus 1 on the interval is given minus 2 to 3. So, find out f dash of x and equate this one is going to be 0. So, this will give you x equal to 0, minus 1 and 2. These are the critical points where the possible local maxima or local minima exist, right. So, find out all these values of this possible. So, you will find out 0, this is minus 1 and this is 2. So, find out corresponding value of f of minus 1, f of 0 and f of 2. So, f of 0 is equal to 1, f of minus 1 equal to minus 4 and f of 2 equal to minus 31. So, these are the 3 points and these are the 3 values the function it has. Now, f of the values of f x at the interval, we had done this, right, 4 minus 31, and find out again minus 2, 3 and so on at random. So, as you can see here, f of 2 attains the minus 31 and f of minus 2 is going to be 33. So, this will be the global minimum value and this will be the global maximum value, and how you identify here from here itself, right. So, you have identified this one. So, f x equal to x minus 2 into sin x on 0 to 2 pi by 2. Do the same thing, find out f dash of x become 1 minus 2 cos x equal to 0 and equate it 0, x equal to giving pi by 3 to 5 pi by 3 in the interval 0 to 2 pi. Find out for each value of f pi by 3 and f of 5 pi by 3, and look at those value. F of pi by 3 equal to in approximate value minus 0.684 and f of 5 by 3 is equal to 6.9680. Obviously, f of 0 points of the intervals at the end points of the intervals. So, f0 equal to 0 and f2 pi equal to 6.28. So, what will be the global local and global minimum value? So, this is the global minimum value and this will be the global maximum value. Why? Because we have to check the end points as well. So, here in the last question, here the question was what was the end points? End points was minus 2 and 3 and these are the 3 points. So, we have to find out at least 5 points, 5 values. Which one? F of 0. Okay. So, let me give you here. So, this is minus 2, this is minus 1, this is 0 and this is 3, right? Is anything f2. Okay. So, we have to 2. So, for this value f of minus 2 is equal to 33, f of minus 1. So, f of minus 1 equal to minus 4. So, f of 0 equal to 1, f of 2 equal to minus 31 and f of 3 is equal to 28, f of 3 equal to 28. Now, compare these 5 values and find out the minimum one. So, which one is the minimum one? Obviously, minus 31 is the minimum one. So, this point f2 will become the global minimum value. And what is the value of global minimum point? That is 2. So, at the 2 x equal to 2, the function attains the minimum global minimum value minus 31. Similarly, find out again the maximum value. The 33 is the maximum value. That is why minus 2 become its maximum value points where the function attained its global maximum, and the global maximum value is nothing but it's a 33. So, that is the things, and similarly you can do for here. We will have 2 points here and 2 points here. Compare these 4 and you will find out that here the critical points become the global maximum and global minimum, not the end points. Similarly, you can find for this is the end points, and f dash equal to 0 will give you x equal to 1 as a critical point. So, these 3 points, you compare these 3 points f1 by 2, f2 and f1, and you will find out the maximum and minimum value. Similarly, you will find out maximum and minimum value for x equal to r. So, domain is given is r, and we have to find out the 3x square plus 6x plus 8, and we will see that f x is always greater than or equal to f minus 1 for all x value. Thus, 5 is the minimum value here, see, of f x, which attains at x equal to minus 1. So, x equal to minus 1 will become its minimum value point, and what will be the minimum value? Minimum value is 5, and similarly so on, right. So, this one is the where do you think the derivative exists here? No. So, the function does not have any derivative, but still we can find out that 1 is the point where the function has the maximum value, right, and what will be the maximum value? Maximum value is 5. Similarly, find the maximum minimum value of sin 3x plus 4, and you will see that it will be the minimum value is 3 and maximum value is 5, right. So, in a similar manner, all these questions are for you given at that, so that you can accommodate, and it's self-explanatory one. So, it's a self-explanatory examples. Just go through it and find out that maxima and minima of a function, and then global maximum and global minimum of a function can be obtained by just using the first derivative of a function. So, thank you so much.